How do we describe motion? Take this ball for example, as I move it from here to here. Through some measure of time and displacement from a given starting point, I can quantify its velocity. But in measuring displacement, we're measuring from a point. Does this point need to be stationary for the laws of physics to apply? Well, no. Which brings me to Einstein's first postulate of special relativity. Einstein's first postulate of special relativity states that all inertial frames of reference are equivalent. An inertial reference frame is defined as a frame of reference that is traveling at a constant velocity, or otherwise defined by the fact that from this reference frame, Newton's first law applies. As you can see, whilst the car is traveling at a constant velocity, the ball is at rest. But as soon as the car accelerates, the ball seems to gain some sort of kinetic energy when no force was acted upon it. This clearly violates both Newton's first law and the law of the conservation of energy. Now that we understand the significance of inertial frames of reference, what is Einstein saying when he says they're equivalent? Equivalence refers to how the motion of objects can be explained from different points of reference. As you can see from both the road as a frame of reference and me as a frame of reference, projectile motion principles can be applied and the motion of the ball is predictable, which evidently supports Einstein's first postulate. Now that we know Einstein's first postulate, let's move on to his second. So let's say we're sitting in the back of a truck and suddenly I decide it's a bit cramped, so what I do is I pick you up and I drop you off the back of the truck. Through summing the vectors of motion, we can see that your velocity relative to the ground is the same as the truck's velocity. Not very nice. But if I'm kind enough to throw you with equal magnitude of the truck's velocity in the opposite direction, then the vectors cancel out and you simply fall maybe a meter, no harm done. With a similar thought process, let's consider a lantern on the back of a truck. Assuming the truck had velocity, we would sum that vector with the speed of light to get the speed of the light coming out of the lantern relative to the ground. Does this mean with enough velocity we can generate stationary light? Well, no. In fact, light and matter act very differently. Einstein states this in his second postulate as the speed of light in a vacuum is constant from all inertial frames of reference. With Einstein's second postulate comes two new concepts called time dilation and length contraction. This equation is used to find the time dilation for an observer inside the reference frame. What this equation can qualitatively tell us is that the faster an inertial reference frame goes, the slower their time will appear. Length contraction is derived from the time dilation equation. What this can qualitatively tell us is that objects in motion will appear shorter than when they were at rest. These concepts can be difficult to understand as us humans aren't used to going the speeds to which these become significant, hence it's not part of our natural physics ability. However, humanity has not been completely unaffected by these concepts. GPS satellites have to account for time dilation as they have relative velocity with the Earth's surface, hence their clocks become desynchronized. Einstein's postulates show us how special relativity can affect the universe. As our technology continues to advance and explore the extremities of physical principles, time dilation and length contraction have become considerable quantities in the analysis of motion. Thank you for watching.